Dear viewers of Akshi.com, by Vetri from Pondicherry. Good evening. Today, I am going to take another topic, the most important topic, that is P block elements. Under the P block elements, the groups start from 13 to 18. That is, P orbital is progressively filled, starting from P1, P2, P3, P4, P5, P6, like that. So all the elements having this progressively filled in P orbital will call it as P block elements. Specific example: Boron family, carbon family, oxygen family, nitrogen family, halogen family, and inert gas elements. Here, let me concentrate first on boron family. What are boron family? The elements that are included in boron family are boron, aluminium, gallium, indium, and thallium. Boron, the symbol B, having the electronic configuration 2s2 2p1. Aluminium, symbol AR, outermost electronic configuration 3s2 3p1. So the general electronic configuration, all the P block elements, ns2 np1. So aluminium 3s2 3p1. Gallium, Ga, represented by symbol 3d10 4s2 4p1. Indium, symbol In, 4d10 5s2 5p1. And thallium, Tl, 4f40 5d10 6s2 and 6p1. That is 6s2, that is 6p1 or the electronic configuration. So the characteristic of electronic configuration of the boron family is boron 2s2 2p1, aluminium 3s2 3p1, gallium 4s2 4p1, indium 5s2 5p1, and thallium 6s2 6p1. This is the interesting electronic configuration regarding the boron family. Right. So let me first compare the general properties, physical and chemical properties of all the elements. Let me compare. What heading? So I am going to compare occurrence, number 1. Number 2, atomic size. Number 3, melting and boiling points. Number 4, ionization energy. Number 5, oxidation states. Number 6, metallic character. I will compare. List continues. Number 7, electronegativity. Number 8, nature of bonding. And number 9, reactivity. So I am going to discuss all these headings, the entire family members I am going to compare, which is more reactive, which is less reactive. All these questions can be answered by knowing these factors. First let me discuss about the occurrence. So among the boron family, boron is a non-metal, whereas other elements are metals. The interesting information. Among the metals, aluminium is the most abundant metal and the third most abundant element after oxygen and silicon is the air. This is the interesting information. Third most element is aluminium. The metal is aluminium. Most abundant metal is aluminium. So after oxygen and silicon, this is the third most abundant metal. Very interesting information. Another interesting information is gallium is twice as abundant as boron. When compared to boron, gallium is twice as abundant as boron. But indium and thallium are much less common. They are not familiar. Much less common. So this is the interesting information regarding occurrence. Coming for the atomic size. We know generally in the periodic table, atomic size increases across the group, decreases across the period. So under this family, boron family, let me compare. Generally, atomic radius increases across the group, boron family, except gallium. Just see, I am giving the value here in Armstrong unit. That is 85, 143, 135, 167, 170. So exception only gallium, 135. Otherwise, it's going on increasing. The interesting information. So, except gallium, generally atomic radius increases across the group. This is the interesting information regarding boron family. Coming for the melting and boiling points. The melting and boiling points of group 13 element. I have already put this as 13th group elements. Do not show a regular trend. It is not showing a regular trend. Generally, melting point decrease from boron to gallium and then increase up to thallium. This is the interesting information regarding melting and boiling points. Coming for ionization energy. What is ionization energy? We know. It is the energy required to remove one electron from the outermost orbital of a neutral gaseous atom to form unipositive ion, gaseous ion. This is called ionization energy. So this ionization, generally ionization energy decreases across the group, opposite of atomic size. So in this case, among the boron family, a deviation occurs at gallium and thallium. So this deviation is due to inability of screening effect to compensate nuclear charge. It is due to the inability of screening effect to compensate nuclear charge. This is the interesting information. So the idea here it is there are exceptions on the gallium and thallium. Another interesting property I want to compare, oxidation state. Oxidation state normally will be given a plus or minus. All the elements in this group have +1 and +3 oxidation state in common. This is the normal question can be asked. The common oxidation state in boron family +1 and +3. Okay. Another interesting information. What about the stability of +1 and stability of +3? Let me compare here. When you move down across the group, +3 oxidation stability decreases. Kindly follow. When you move down from the top to bottom, boron, aluminum, gallium, indium, thallium, the stability of +3 decreases. What about +1? Whereas +1 stability, oxidation stability increases. So when you go for gallium, indium, thallium will be more stable. +1 is more stable than +3. This is the interesting information. So this is again due to inert pair effect. What is inert pair effect? That is electron present in s orbital which is not involved in bonding. So that pair we are calling it an inert pair. So that is this is because of this inert pair effect. So we are having this particular effect. Okay, the next one. Metallic character. Another interesting comparison I can do with this metallic character. Metallic nature of elements increases from boron to aluminum, but that decreases from aluminum to thallium. So this is the interesting information. Gallium, indium and thallium do not continue the trend because again poor shielding by d electrons. So again it's not a smooth, the trend is not smooth in the metallic character also. Number 7, electronegativity. Electronegativity, this is another interesting parameter, property, periodic property. So just look at the value, boron 2.04, aluminum 1.61, gallium 1.81, indium 1.61, thallium 1.62. So students, you are not necessarily have to memorize, but the trend you must memorize. Here, generally electronegativity decreases across the group, but the trend is not regular. So just to compare, exceptionally, gallium is showing exceptional case. So generally, electronegativity decreases because this is according to the other groups. Generally, in all the groups, electronegativity decreases across the group, increases across the period. So this group, boron family, also obeys that, but the exception is gallium. Another interesting property, bonding, the formation of covalent and ionic bonding. So in this case, boron family, generally the tendency of forming covalent compounds decreases. This is interesting information. Tendency of forming covalent compound decreases. Consequently, the compounds of boron 3 plus are predominantly covalent in nature. Boron 3 plus is predominantly covalent in nature, while Al 3 plus, gallium 3 plus and indium 3 plus and thallium 3 plus compounds are ionic in nature. This is the interesting information. So the covalent character decreases when you move down across the group, whereas ionic character increases. This is the comparison I want to give. This is the interesting information I want to give regarding bonding. Now let me come for the reactivity, another important reactivity of the metal, reactivity of the compounds. So under the first one, boron, first member, boron. So it is in the allotropic form. So amorphous boron is reactive, but the crystalline boron is comparatively unreactive. This is the interesting information I want to give regarding for reactivity of boron. So just what is the action? Reaction with air or oxygen. Amorphous boron burns in air oxygen forming oxide. Boron, oxide. What about aluminum? Aluminum burns readily in air to form oxides, which is exothermic. Gallium, indium, thallium are stable towards air. So the reactivity towards air, it is decreasing. This is the interesting information. Reaction with other elements, not only air, with other elements. Boron reacts with the nitrogen to form nitride, boron nitride. With the halogen, it forms trihalide, boron BX3. This is the interesting information. Whereas aluminium bonds in nitrogen at a high temperature to form ALN. It's also form aluminium also bonds, but at a high temperature to form ALN. And the other elements do not react. So again, reactivity decreases with the other elements also. This is the interesting comparison you must do. A reaction of acids. Amorphous boron dissolves in hot concentrated nitric acid and sulfuric acid to form boric acid, H3BO3. This is the interesting information. Just look here. Boron reacts with the 3 moles of nitric acid, concentrated nitric acid, to give boric acid and 3NO2. H3BO3 is nothing but boric acid. The same way, again 2 moles of boron again reacts with 3 moles of sulfuric acid to produce 2 moles of boric acid and 3 moles of SO2. So in both cases, hot concentrated nitric acid, sulfuric acid, boric acid is common. So in the case of nitric acid, NO2 is formed. In the case of sulfuric acid, SO2 is formed. That is the only difference. Okay. What about other metals? Aluminium dissolves in mineral acids, liberating hydrogen. This is the way. So aluminium still gives aluminium chloride and hydrogen is liberated. So this is the interesting information I want to give you. However, concentrated nitric acid renders the metal passive with other metals. All the remaining 3 metals dissolve in hydrogen acid, liberating hydrogen. So this is the interesting information I want to record here. Coming for the action of alkalis, I can compare the properties. But when boron dissolves in fused alkali, forming borates with the evolution of hydrogen. This is the interesting information. So boron dissolves in fused alkali, forming borates with the evolution of hydrogen. For example, 2 moles of boron reacts with 6 moles of sodium hydroxide to form 2 moles of Na3BO3 and 3 moles of H2. This is the interesting information. Sodium borate is formed, 3 moles. So what about aluminium? Aluminium also dissolves in aqueous solution, sodium hydroxide, liberating hydrogen and forming aluminate, the corresponding sodium aluminate. So this is the interesting information I want to give. So boron gives borate, corresponds sodium borate, aluminium gives corresponding sodium aluminate. What about other metals? Like aluminium, other metals dissolve in aqueous sodium hydroxide, liberating hydrogen and corresponding salts they are forming. This is the comparison. Okay. So with this general comparison, so now I will enter the specifically extraction of boron and properties and the importance of few compounds I will discuss under the boron family as per the CBC syllabus. Coming for the ores of boron, what are the ores of boron commonly available? Boric acid, H3BO3 is a ore. Borax, that is Na2B4O7 dot 10H2O. Sodium tetraborate, that is decahydrate. And colemanite, another important ore, Ca2B6O11. So these are the common ores available for boron. So let me take now boron specifically and I will extract from colemanite or borax. Specific example, on a large scale industrially, boron is extracted from its minerals borax or colemanite. Either from borax or from colemanite, I can extract boron. Kindly follow. So colemanite is converted into borax by boiling with a dilute solution of sodium carbonate in the requested proportion. So if you take a required quantity of sodium carbonate and corresponding water, so the corresponding colemanite will be converted into sodium metaborate. See the equation here. 2 moles of Ca2B6O11 reacts with the 3 moles of NO2CO3, presence of 1 mole of H2O produces 2 moles of sodium metaborate, Na2B4O7, 3 moles of calcium carbonate and calcium hydroxide 1 mole. So it is converted into, that is corresponding borax. This is the interesting information. Okay. But the next step. So this, here the insoluble calcium carbonate form settles down and the borax is crystallized from the molten liquor. From the molten, so after calcium carbonate settled down, we can filter it off. The borax is crystallized from the molten liquor. So boron is isolated from borax in the following two steps. So from the borax, so we can extract boron by following the two steps. What are the steps? Step 1. Borax is treated with hard concentrated HCl when the sparingly soluble boric acid slowly separates out. So first we'll give, that is the metaboric acid, and the tetraboric acid, and from that we are getting the boric acid. Can you see here? So Na2B4O7 reacts with 2 moles of HCl to produce H2B4O7 and 2 moles of sodium chloride. First step. Again in the step 1, first stage. And what will happen now? This H2BO4O7 and reacts with 5 moles of water to produce 2 moles of H3BO3. So we are getting in step 1 boric acid, H3BO3 from boron, sodium metaborate. That is the step 1. The second step. So when boric acid is heated strongly, boron trioxide is obtained in the first step again. So this boric acid that we are getting in the step 1 on heating to produce B2O3 and 3 moles of H2O. So we are getting in the first step B2O3, right? So from B2O3 we are going to extract boron, that is step 2. What way? Step 2 is conversion of boron trioxide to boron. When boron trioxide is heated in a crucible to bright redness with magnesium, with a very strong bright redness with magnesium, when you heat, a dark brown powder of amorphous boron is obtained as a residue. Very, very interesting information. So after getting P2O3 from the step 1, so when you heat with magnesium to bright red hotness, so it is converted into correspondingly boron. So B2O3 reacts with the 3 moles of Mg to produce 2 moles of boron and 3 moles of Mg. So this is the way we are getting boron from aluminides. So what is the method? That is pure boron, how to prepare? That is a specific method that also I will discuss. Preparation of pure boron. What way? Pure boron is obtained in the crystalline form by passing a mixture of boron tribromide vapors and H2 over electrically heated filament of tungsten at 1470 Kelvin. So when you pass a mixture of boron tribromide and hydrogen over electrically heated filament of tungsten, these vapors at 1470 Kelvin will get a very, very highly pure, the 100% pure boron we are getting. This is the interesting information regarding the preparation of pure boron. Next, let me go for the properties. Properties of boron. Physical properties first let me discuss. Boron exists in 2 allotropic forms. That is amorphous boron, which is brownish black powder. Another is crystalline boron, rhombohedral form. These are 2 allotropic forms of boron. So it is a non-metal and it undergoes sublimation during melting. So when we are melting, it undergoes sublimation. This is regarding for physical property. Coming for chemical. So first let me take action of air. Air means we know it's a mixture of nitrogen and oxygen will be there. So it has no reaction at ordinary temperature. This is interesting information. At ordinary temperature, boron will not react with air. But at very high temperature, what is the minimum temperature? But at 975 Kelvin, it burns in air to produce boron trioxide and a little boron trinitride. So with the oxygen boron trioxide, with the nitrogen boron nitride, these reactions are 4 moles of boron reacts with the 3 moles of oxygen to produce 2 moles of B2O3, and 2 moles of boron reacts with 1 mole of N2 giving 2 moles of Bn. So this is the interesting information regarding action of air with the boron. So the conclusion is at ordinary temperature it will not react, but 975 Kelvin and above it will react to produce a mixture of B2O3 and Bn. This is the interesting information I want to record. The number 1 reactivity. Action of acids. Amorphous boron dissolves in hot concentrated nitric acid and sulfuric acid to form boric acid. Amorphous boron dissolves in hot concentrated nitric acid and sulfuric acid to form boric acid. This is the interesting action of acid. So number 1. boron reacts with 3 moles of concentrated nitric acid to give boric acid and 3 moles of NO2. The 2 moles of boron reacts with the 3 moles of sulfuric acid, again producing boric acid and 3 moles of SO2. So this is the interesting information I want to give regarding action of acids. Action of caustic alkali. So what will happen is, it dissolves in fused alkali forming borates with the evolution of hydrogen. This is the very interesting information. It dissolves in fused alkali forming borates with the evolution of hydrogen. So 2 moles of boron reacts 6 moles of sodium hydroxide to give, that is 2 moles of Na3BO3, sodium borate, 3 moles of H2. This is the interesting information regarding caustic alkali. The next one, action of metals. Except copper, silver and gold, all metals combine with boron at high temperature in the electric furnace to form borides, corresponding metallic borides. Except copper, silver and gold, all other metals combine to form the corresponding boride. This is the interesting information. Okay, next one, action of non-metals. Boron combines with N2, Cl2, Br2 and carbon at high temperature. Kindly follow, always reacting at high temperature, forming boron nitride, Bn, boron trichloride, BCl3, boron tribromide, BBr3 and boron carbide, B4C respectively. This is the interesting information we can. Now, the next one is another important characteristic property regarding for activity, action as a reducing agent. Boron is a powerful reducing agent. What will we say now? Boron is a powerful reducing agent and can even replace carbon from carbon dioxide and silicon from silica. So just, if you want to understand this reducing action, just see the reaction given below. What way? 4 moles of boron reacts with 3 moles of carbon dioxide to produce 2B2O3 and carbon is getting out, that is coming out, replaced. So carbon from carbon dioxide is replaced. The same way, 4 moles of boron reacts with 3 moles of SiO2 to produce 2 moles of B2O3, again 3 moles of Si. So Si is again coming out from SiO2. That means the boron replacing carbon from carbon dioxide and silicon from silicon dioxide. This is the powerful action of reducing agent. Interesting information regarding boron. So this is regarding for boron. Now let me discuss the compounds of boron. Under these compounds of boron, let me take specific boron, sodium tetraborate, Na2B4O7. This is the interesting information. How to prepare this borons? Preparation, I can prepare from colemanite. Colemanite is another word. I can extract, I can prepare borons, sodium tetraborate. When colemanite is heated with concentrated solution of sodium carbonate, borax is formed. Very simple reaction. So what is the formula for the colemanite? Cl2B6O11. That is the molecular formula for colemanite O. So 2 moles when you heat with 3 moles of sodium carbonate, then we are getting borax. Sodium tetraborate, Na2B4O7, 2 moles of calcium carbonate and 2 moles of metaborate, NaBO2. Metaborate is formed. So this is the interesting information. Okay, so this metaborate again we have to convert into borax. What way? Just see the reaction. On filtration and concentration, crystals of borax separate. So after filtration and concentration, we can get the borax crystal. Right. So to the remaining mother liquor, the current of carbon dioxide is passed through the mother liquor to convert the metaborate into borax. So in the original reaction we have seen metaborate is formed. That metaborate can be converted into borax by passing carbon dioxide. So this is the reaction. So this is the formula, sodium metaborate. 4 moles of NaBO2 reacts with 1 mole of carbon dioxide to produce Na2B4O7, borax, sodium metaborate, tetraborate. So in this case, Na2CO3 again is formed along with. So from metaborate we are getting the borax. So the interesting information is again sodium carbonate is produced here. So the residual sodium carbonate used again and again for the treatment of the fresh quantity of polyamide. So this sodium carbonate formed here, we can recycle to extract more and more of polyamide to convert it to sodium tetraborate. This is the interesting information I want to give. The next one. Properties. As usual, first I will discuss physical properties of sodium tetraborate. Borax exists in three forms. This is the interesting information. They exist in three forms. What are they? Prismatic borax, Na2B4O7 10H2O. Octahedral borax, Na2B4O7 5H2O, and borax glass anhydrous. So these exist in three forms. Okay. Coming for chemical properties. First let me take action of heat. When prismatic borax is heated above its melting point, until all the water of crystallization is expelled, it forms a colorless glassy substance known as borax glass. So I have already pointed out. First one, 10 water molecules. And second one, 5 water molecules. Third one is without any water molecule. So when we are, that first one, prismatic borax is heated above its melting point, until all the water of crystallization is expelled, it forms a colorless glassy substance known as borax glass without any water. Okay, on further heating, it decomposes to give sodium metaborate and boron trioxide. Even that sodium metaborate, the tetraborate, further react, that heating, it decomposes to give sodium metaborate and boron trioxide. This is the interesting information. Just see the reaction. This is the original Na2B4O7 10H2O. So on action of heat, first produces sodium tetraborate and 10 water molecules removed. So we are getting this anhydrous, and this anhydrous again sodium tetraborate. On further heating, we are getting sodium metaborate and B2O3. So this is the interesting information. So question can be asked. Kindly follow me. The next one. Under this, the most important information is borax bed test. This commonly question can be asked. The metal ions can be identified by doing borax bed test. What is this test? When this mixture is fused with metallic oxide, it forms characteristic colored beds. With the help of color of the metal ion, the color of the metal ions can be identified. So when the mixture is fused with metallic oxide, it forms characteristic colored beds. This is the first information. So with the help of the color, from the color noted in the oxidizing flame or reducing flame, the metal ion can be identified. A specific example here, copper oxide reacts with B2O3 to form CuBO2 twice. So this is the color. This will produce a color. The oxidizing flame one color, reducing flame another color. So the same way all metals will combine with B2O3 to form corresponding beds. Colored beds will form. So I will give the list, you can see that. It will be very interesting. So so this borax bed test can be done easily by platinum loop in the laboratory. What way? You take a platinum loop, just introducing a pinch of borax, heat in a platinum, and it gives after heating you will get a colorless glassy bed. It's again dipped in a colored metallic salt solution and again heat a characteristic colored bed. Very, very simple. So let me repeat it. So this can be done by platinum loop also. So take a platinum loop. What way? When a pinch of borax is heated in a platinum loop. So first it touches borax and heat in the flame. It melts to give colorless glassy bed in the platinum loop. So colorless glassy bed will be formed in the platinum loop. And it is again dipped in colored metallic salt solution. So it will react now with glassy bed with metallic salts. So the corresponding, the colored beds will form. So, and again it will heat. So characteristic colored beads are formed just like copper I have shown you. So different color for different cation. So from this we can easily identify the metal ion. So let me give you the list so we can appreciate the interesting information. Kindly follow. So here from the color of the beds, the basic radicals can be identified as follows. For example, I have already given copper salts give blue beds in oxidizing flame and red beds in reducing flame. Even if that you might have already studied your 9th and 8th and 9th standard, the flame. So there are two portions in the flame. One is oxidizing flame, another is the reducing flame. the two different regions. So in the two different regions, if you show, you'll get a two different colors. That I can give the list here. Kindly you can appreciate. Now what is the interesting information? So this is the first list, metals. Here color in oxidizing flame, color in reducing flame. I am giving the list. Kindly follow. Students, you have to memorize this color because questions are there competitively. So copper will give blue color in oxidizing flame, whereas it gives red color in reducing flame. Very, very interesting information. So blue color in oxidizing flame, red color in reducing flame. The same way, iron gives yellow color in oxidizing flame, bottle green in reducing flame. So iron gives yellow color in oxidizing flame and bottle green in reducing flame. Second interesting information, iron. So manganese, another metal ion. So they are pinkish violet in oxidizing flame and colorless in reducing flame. Colorless in reducing flame. Coming for cobalt, another interesting basic metal we can identify. So will be in both cases it's giving blue color. That is blue color in oxidizing flame as well as in reducing flame. So whenever we get blue means we'll think of cobalt. Chromium, another interesting. Chromium gives both cases green color. That is green color in oxidizing flame as well as in reducing flame. The last one, nickel ion. So nickel ion gives brown color in oxidizing flame and grey color in reducing flame. So this is the interesting information I want to record. So what you have to do? So you have to memorize this color of the metal ion in oxidizing and reducing flame. Then you can answer a number of questions, competitive questions. Okay, coming for structure. What is the structure of borax? Borax is made up of two triangular and two tetrahedral units in the form of iron given. So I am going to show the structure. Kindly follow. This is the interesting information. Two triangular and two tetrahedral units are present in this form of iron. And it is containing 8 water. The remaining 8 water molecules are associated with the 2 sodium ion. Thus, borax will be better formulated as Na2B4O5 OH 4 times 8H2. So normally what we are writing, that is, we are writing as Na2, the corresponding B4, the correspondingly, that is O7, and the 10H2O we are writing. Instead of that, so we will represent the correct way, Na2B4O5 OH 4 times 8H2O. So this, if you want to appreciate this formula, just look at the structure here, you can. This is the structure of borax, the ion. B4O5 OH4 2 minus. See here, this is the two triangle. Kindly look at here. One triangle, and this side, this is another triangle. This is the interesting two triangle. And just see here, the top one a tetrahedron and bottom one again a tetrahedron. So this boron with respect to this triangle, this boron, this triangle, whereas this boron tetrahedron, this boron is a tetrahedron. So this is the interesting information I want to give. Kindly follow. Borax is made of two triangle and two tetrahedral units in the form of ion given. That's why I am showing here. So this boron, this triangle, this boron, this triangle, and this boron, this tetrahedron, this boron again tetrahedron. So this is, so remaining 8 water molecules, again it is not shown here, sodium ions, and for the 8 water molecule it is not shown. That 8 water molecules are associated with the central sodium ion. So this is the actual structure of sodium, that is borax. The very, very interesting information regarding for the structure. Coming for the uses, it is used to identify metallic radicals in qualitative analysis. First important use. It is commonly used to identify metallic radical in qualitative. Just now I have explained you borax bed test. By using a platinum loop, we can easily test in the laboratory. A number of cation can be identified. So to identify metallic radical in qualitative analysis we are using. Number 2, as a flux in welding metals. During welding metals we are using as a flux, this one, this compound we are using. Third important use. It is used in the manufacture of glass, soap and porcelain we are using this sodium metabolic. And 4, it is also used as a cleaning, dyeing agent in tanning industry. Cleaning and dyeing agent in tanning industry also we are using. And as food preservative again, so we are, that is the another interesting in the application of sodium metabolite. Now, next compound is the most important, orthoboric acid. This is the another interesting compound, orthoboric acid, H3PO3. So let me discuss again preparation properties and important uses of orthoboric acid. Preparation. We can prepare from borax, just as I discussed, sodium metabolite. Orthoboric acid can be prepared by heating hard concentrated solution of borax with the calculated quantity of concentrated acid, sulfuric acid commonly. On allowing the liquid to cool, crystals of boric acid are deposited. Very, very interesting method we can prepare. So what is the corresponding reaction? NO2B4O7. When you treat with sulfuric acid, that is the concentrated sulfuric acid, so it reacts in presence of 5 water molecules to produce sodium sulfate and boric acid is formed. So we are getting the crystals of boric acid. Interesting information. Okay, coming for the properties. First, let me discuss physical properties. It is a white crystalline substance, soft and soapy to touch. Very interesting. It is slightly soluble in cold water, but more in hot water. So it is slightly soluble in cold water, soluble regarding solubility, cold water, but more in hot water. Right. Coming for the chemical property. Action of heat. First, let me discuss. On heating, boric acid or orthoboric acid above 370 Kelvin forms metaboric acid, HbO2. So H3PO3 gives HbO2, and this metaboric acid on heating further yields boric oxide, that is B2O3. This is the interesting information. So boric acid, orthoboric acid on action of heat produces, that is metaboric acid, HbO2, and which on further heating produces B2O3. This is the interesting information. Right. Coming for the action of water. What happens when you treat orthoboric acid with water? It is a weak monobasic acid. Kindly follow, it's a weak monobasic acid, but it is not a protonic acid. That is the interesting information. It is not a protonic acid. It is not, there is no replaceable hydrogen. So, but acts as a Lewis acid by accepting electron from a hydroxyl ion. This is the interesting information. So 2H2O plus H3BO3 giving BOH4 minus H3O plus. So this is metaborate ion. The interesting information. Next one, action of alcohol. Actually, this is we can use as a test for boric acid. If you want to test for boric acid, actually we can use this action of alcohol. Even alcohol we can test by this. Identify with the help of boric acid. A mixture of ethyl alcohol with boric acid burns with green energy flame due to the formation of ethyl borate. So even we can test for alcohol. Right. So what happens in this reaction? 3C2H5OH reacts with H3BO3 to form the corresponding BOC2H5 thrice and 3H2O. Ethyl borate is formed. So which is responsible for the green color, green edged flame. So we can easily identify. So I already found that a test for boric acid already, it returns, how to test again boric acid? It returns turmeric pepper brown, which turned blackish on dipping in sodium hydroxide. So turmeric pepper turning brown, further if you dip it in sodium hydroxide becoming black. So this is the test for boric acid. I hope this will be enough for boric acid. What we are seeing is the structure of orthoboric acid. Kindly see, this is the, imagine, this one molecule. So again, you just imagine it's going on connected with through hydrogen bonding. This is actually the structure of orthoboric acid. Okay, the next one. Uses, coming for uses, let me discuss. It is used as an antiseptic in medicine. The very, very interesting information. It is used as an antiseptic in medicine. Orthoporic acid, boric acid. Second, it is used as a preservative of food. 3. It is used in making enamels and water glasses. It is used. Finally, it is also used in glass industry. Boric acid is used. Very, very interesting information regarding uses. Let me go for the next one. That is diboron, another important compound of boron. Diboron. How to prepare diboron? Simplest method is, the simplest boron hydride is known as diboron. B2H6 is called diboron. That is the formula. So how to prepare? So I can now show the laboratory method. It can be prepared as follows. In the laboratory, it can be prepared from sodium borohydride. From sodium borohydride, we can prepare very easily in the laboratory. What is the method? Kindly question can be asked. What is the method of laboratory method for the preparation of diboron B2H6? The first method is oxidation of sodium borohydride by iodine gives diboron. Oxidation of sodium borohydride by iodine gives diboron. Chemical reaction. 2 moles of NaBH4 reacts with 1 mole of I2 to produce 1 mole of B2H6, that is diboron, 2 moles of NaI and 1 mole of H2. So we are getting diboron from sodium borohydride by simple treatment with the iodine. So action of iodine, you can get the sodium borohydride in the laboratory. Second, another industrial method, commercial method. So again, boron trifluoride. From boron trifluoride, we can prepare large scale. We can prepare large scale. That is, boron trifluoride reacts with sodium hydride to produce diboron. So 6 moles of NaH reacts with 2 BF3 at 450 Kelvin produce B2H6. That is 6 moles of NaF it is forming. So we are getting again diboron. Now coming for the physical properties. It is a colorless, highly toxic gas with a boiling point of 180 Kelvin. It is a colorless, highly toxic gas with a boiling point of 180 Kelvin. Very, very, because a gas. Right. Coming for the chemical property. Action of air. It catches fire spontaneously upon exposure to air. So when you keep in the air, it catches fire. Immediately diboron catches fire. So what's happening now? It burns in oxygen present in the air, releasing an enormous amount of energy. So the corresponding reactions are B2H6 reacts with the 3 moles of O2 present in the air to produce B2O3. That is boron trioxide and 3 moles of H2O. With the enormous amount of energy is released. This is the interesting information regarding action of air. Second important action of water. Diboron again undergoes hydrolysis. What way? Diboron undergoes hydrolysis in water to give boric acid, orthoboric acid. Very, very interesting reactions. Can you follow? B2H6 reacts with the 6 moles of H2O to produce orthoboric acid and the 6 moles of H2O. This is the interesting information regarding action of water. Let me go for the action of Lewis bases. Diboron undergoes cleavage reactions with Lewis bases to give boron adducts. Simply adduct is forming like PH3.L. L is nothing but indicating the adducts. What are the adducts here? So here trimethylamine and carbon monoxide are commonly used as an adduct. So you see the reaction. B2H6 reacts with 2 moles of NCH3 thrice to form 2PH3.N CH3 thrice. The same way another adduct. P2H6 reacts with 2 moles of CO again forming an adduct 2PH3.CO. So in both cases, trimethylamine and carbon monoxide, it forms adduct. This is the interesting information, that is action of Lewis bases. The next one. Action of ammonia, another very, very interesting reaction commonly asked in the question paper or India competitive examinations. Reaction with ammonia. Reaction of ammonia with the diboron gives initially B2H6.2NH3. But reacts with ammonia, 2 moles of ammonia react to give this. But you can write the structure this way. BH2NH3 twice plus and BH4 minus. You can write in the form of positive and negative ion. Further, the ion further heating gives borosine. Kindly follow. B3N3H6, borosine. It is also known as inorganic benzene or borosole. Often question can be asked, what is inorganic benzene? Nothing but borosine or borosole. The molecular formula, it is B3N3H6. It will behave like a benzene. Structure is also like a benzene. So I will show the structure, kindly wait. So now, what is the corresponding reaction here? 3 moles of B2H6 reacts with the 6 moles of ammonia to produce this molecular formula. 3 B2H6 dot 2 NH3. So, or I can write the same structure like this: BH2NH3 twice plus and BH4 minus, the corresponding 3 moles. So, okay. So, what happened now? In this case, so this structure 3 B2H6 2NH3 on again, when we are further heating, converted to the correspondingly inorganic benzene, borosine or borosole. So 2 moles of B3N3H6 plus 12H2 it is forming. This is the interesting information. So just see the structure of the inorganic benzene. Can you see here? It is an alternative just like a benzene. Single bond, double bond, single bond, double bond, single bond, double bond. Just like benzene, it is there. This is the interesting information. In all the cases, again, hydrogen is there. This is the benzene structure. The only difference here, here in benzene, all the cases, carbon is present. Carbon, 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 carbon. But in this case, inorganic benzene, alternatively nitrogen, boron, nitrogen, boron, nitrogen, and boron. That is the only difference between. That's why we are calling it as inorganic benzene, borosole. This is the interesting information regarding this. The next one. So let me discuss the structure of diborane. Here in structure of diborane, the 4 terminal hydrogen atoms and the 2 boron atom lie in the same plane. This is interesting information. So if you look at the structure, you can have an idea. So kindly imagine there are terminal 2 hydrogen atoms and 2 boron atom lie in one plane, and above and below this plane there are 2 bridging hydrogen. One is above, one is below. So this is confirmed by Raman spectra. What we are seeing here, this is the structure of diborane. Kindly follow. So this boron and this boron, 2 hydrogen and 2, everything they are in the same plane. Whereas above the plane 1 hydrogen, below the plane another hydrogen. This is the actual structure of diborane. Another interesting information, the bond angle between HB, and this is 97 degree, and outside it is bond angle, it is 120. Boron hydrogen distance between boron and this hydrogen, bridged hydrogen, is 134 pm picometer, and in this case, this boron hydrogen distance, it is 119 picometer. This is the interesting information. Another interesting information, between these 2 boron, that is the value also, it is the experimentally determined, it is 117 picometer. Yeah. This is the interesting information regarding diborane. I hope you have enjoyed the lecture.